Hello everyone, this is chapter 3.5, which is a section on implicit differentiation. The first thing I want to get out of the way is what exactly it means for an equation to be in explicit form versus implicit form. Now here I say, well, explicit basically means that y can be solved for and completely isolated in terms of the other variable x, where it is in implicit, it's not or it's impossible. So here, y is all in terms of x for this first example. For the second one, it's also in terms of x. There's a plus or minus, but it's still completely isolated. In fact, this second example is really just the same equation here for the first implicit example. If you get y squared by itself by subtracting x squared to the other side and then square rooting both sides, you get y is equal to plus or minus this. So this is an implicit version of this explicit equation. All right. The second one, though, is a little different. This says sine of xy equals x squared minus 2y. Now, in this case, it's basically impossible to get y by itself. There are some things you can try to do, but it's almost impossible. So you can, let's say, take sine inverse of both sides to get xy, but then now this negative 2y is trapped inside of the sine inverse. So there may be some trickery you can possibly do to get y by itself, but in any event, implicit is the case where y is not completely isolated, and trying to isolate and doing so and isolating may not be possible. So isolating y may not be possible, kind of like in the second example. So here's what I have to say about what actual implicit differentiation means. Basically what we're trying to do is we're trying to extract dy dx, which is the derivative of y with respect to x, from an implicit equation, which can actually, believe it or not, basically always be done. So let me just read what I have to say here. So I say, since y is a function of x, by the chain rule, this must be true. The derivative with respect to x of any function of y is, let's say it's g of y, is g prime of y, the derivative of the function of y with respect to y, times, that should be a times, y prime, where y prime is just dy over dx. So this is exactly what the chain rule says, only specifically it's when you have a function of y. So we're actually going to take a look at an example now, and in fact, let's do these two and let's see how it works. All right, so for these two examples, we're asked to find dy dx. Now, again, the main goal is to get the dy dx by itself. So what I'm going to do is differentiate both sides of this equation with respect to x. So this is how it's going to look. I'm going to get d over dx of the left side is equal to d over dx of the right side. Now, derivative of a sum is the sum of the derivatives. Derivative of x squared is 2x. Derivative of y squared from the sentence I just read earlier is the derivative of y squared with respect to y, which is 2y. But then multiplied by derivative of the inside, which is the derivative of y with respect to x, which is y prime. Now remember, y prime means dy dx. So once we solve for y prime, we'll be done. And of course, on the other side, derivative of 4 is just 0. Subtracting 2x will give us, let's see, 2y y prime equals negative 2x by subtracting 2x to the right. And then finally dividing by 2y, well, the 2's cancel. And we just get y prime is equal to x over y, negative x over y, in fact. So we get y prime, which I'll now write as dy over dx, is equal to negative x over y. Now why I choose to write y prime each time until the very end isn't super obvious right now, but in practice it'll become more obvious. In fact, with this one, I think you're going to see why, because otherwise we'll write, this is too much writing basically. We'll write dy dx maybe 5 or 6 times. Opposed to writing y prime, it just makes it a lot quicker. So it's kind of shorthand. I want to also, because remember we could solve for y explicitly with this first example like we saw previously. So I want to do that. I want to solve for y explicitly and then take its derivative and compare. But before we do that, let's take care of this example. So using this idea, let's see what happens. So derivative of sine is cosine. Remember, we're taking derivative of both sides. So it's cosine of the original inside multiplied by derivative of the inside by chain rule. Now, derivative of the inside is, well, it's not very obvious at first hand, like at first glance. But x times y is a product, so we need to use the product rule. Derivative of the first is 1 times regular of the second plus regular of the first times derivative of the second. Derivative of y with respect to x, we're just calling y prime. Okay, perfect. So now what? Derivative of the right now, because we're taking derivative of each side, of each term, basically. Derivative of x squared is 2x. Derivative of negative 2y is just negative 2, but times y prime. Okay, so I hope that's okay. Now we want to get y prime by itself. So to get y prime by itself, what I'm going to do is first I'm going to distribute this quantity here into each of these. So let's see what we get. We get y times cosine of xy plus, let's say xy prime cosine of xy equals 2x minus 2y prime. That's supposed to be 2x. Perfect. So again, we want to get y prime by itself, and what are the y prime terms? It's this one and this one. So I'm going to add this to the right and simultaneously subtract this non-y prime term to that side. So here's what we'll get. We'll get 2y prime plus xy prime cosine of xy equals 2x, and then again, this guy here is a non-y prime term, just like this one is. So I'm going to subtract that to the right. So it's minus y cosine of xy. Perfect. We're so close. All we need to do now is recognize that these two terms both have y prime in common, so we can factor it out as y prime outside of 2 plus x cosine of xy equals the original right side here. It's unaffected. Perfect. Now what we have to do is divide both sides by the non-y prime term, non-y prime factor that it's multiplied to. So 2 plus x cosine of y to both sides. So I hope that's not cut off. Good. Now, let's see. So on this side, these cancel. So we get y prime by itself, which I'll write over here. Now remember, y prime is now isolated, and y prime is our shorthand notation for dy over dx. So now we have dy over dx is equal to just this, which is 2x minus y cosine of xy over 2 plus x times cosine of xy. Perfect. Perfect. That's cut off a little bit from the screen, but we can see it here anyways. I'm just rewriting that part. So now I'm going to redo one, but a different way. I'm going to explicitly solve for y because we can. Remember, here we can't do that, but I'm going to compare so we can see that we do indeed get the same result. So let's take a look at that. So I've erased the work for the second example just to show. For this example, again, we want to get y by itself first, and we saw that when we do that, you get y squared is equal to 4 minus x squared by subtracting x squared to the right, and then taking the square root of each side leaves you with y only on the left, but then plus or minus the square root of the right side. Perfect. So this is a different way of doing this. Let me write or, and this is the explicit way of doing it. Because here in this case we actually can solve for y explicitly. And to find the derivative of this, well, we don't like square roots for derivatives. What do we like instead? 1/2 powers. Awesome. So now let's see. So then the derivative of y, dy dx, is just applying the chain rule with the power rule, with a plus or minus. Plus or minus is okay, I think, because no matter if it's plus or minus, it's just a constant. So the plus or minus we're going to treat like a 2 or 5 in front, just something like that. So we get plus or minus, applying the power rule, 1/2 of the inside to the negative 1/2. Inside stays the same, 4 minus x squared, multiplied by the chain rule, derivative of the inside, which is derivative of 4 is 0, derivative of negative x squared is negative 2x. there's some cancellation of these 2's. Now the negative doesn't really screw things up too much. In fact, if you multiply the negative to the plus or minus, it becomes a minus plus. But I'm not going to do that. Instead, what I'm going to do is I'm going to rewrite this in a little bit of a different way, just to compare. So I'm going to pull the negative out in front. This x that's left over, I'm going to write on top of this this fraction as the numerator. And since this power here is negative, it's really in the denominator, and 1/2 means radical. So we have a radical in the bottom. And now that plus or minus, since a plus or minus is just a sign, and for a fraction you can attach a sign to either top or bottom or even out in front, we're going to attach it to the bottom part. And why am I writing it in this weird way? Well, I'm writing it in this weird way just to show us, to compare that this is indeed true. Because, I hope you agree, the top is x, it's a negative fraction, and the denominator is just y. This quantity here is exactly what y is equal to. So in fact, it is true that our derivative is negative x over y. We just saw it in a different way, so that's a check mark there. Great. So that's all I wanted to show here, and now I'm going to do one more example, but it's going to be a little different. We're going to be finding the equation of a tangent line of an implicit equation, so that'll be fun. And then after that, I'm going to take a look at something new, some new rules that emerge from implicit differentiation. So let's take a look. All right, so now for this example, we're asked to find the equation of the tangent line for this curve at the given point 1, 1. And as it turns out, this actually can be explicitly solved for. So if you want to solve for y, you can try it, but I'll tell you right now, it's not very easy to do so, but it is possible. But I'm not going to do that anyways, I'm just going to use implicit. So let's see if we can follow. So derivative of each of these terms with respect to x are in the order, in this order. Derivative of x squared is 2x. xy, remember x times y, we need product rule. So it's 1 times y plus x times y prime, just like we got before. Derivative of y squared is 2y, but we need y prime. Basically, anytime you take derivative of something involving y, always attach y prime. So that's kind of, in a nutshell, what 3.5 is really all about. Okay, equals derivative of 3 is 0. And yeah, these two involve y prime. I'm going to subtract these to that side and simultaneously pull y prime out from these terms. So we get this, and subtracting those over there, we get negative 2x minus y divided by x plus 2y. X plus 2y. I think we're in okay shape. So now we have y prime, which again is just dy dx. So let me write that over here. We found out that dy dx is equal to negative 2x minus y over x plus 2y. So I missed a 2 here when I rewrote it. But anyways, there we go. Now, I didn't really talk about too much of what we're trying to do here. I just jumped into it and found dy dx. Now, we want to find the equation of the tangent line, and let's recall that to find the equation of a line, you need the slope and the point, to use point slope, and derivative of a function evaluated at a particular point, let's say this point x comma y, 1 comma 1, is the slope of the tangent line. So the first thing we're going to do here is we're going to find our slope m, and all I want to say is that that's dy dx evaluated at the point that we're using here, which is 1 comma 1. This is also known, if you recall, as the point of tangency. So basically what I want to do is I want to plug in x and y to be these values, 1 and 1, to this equation here for the derivative. So it's going to be 2 times 1, so let me write it out. Negative 2 times 1 minus 1 over 1 plus 2 times 1. So we end up getting this negative 3 over 3, which is negative 1. So we have our slope. Our slope is negative 1. So let me write it. There we go. Now all we need to do is use point slope. Point slope is y minus the y value, 1, equals the slope we just found, negative 1, times x minus the x value, which is also 1. Perfect. Distribute add 1 to the other side. So now we have y is equal to negative x plus 1, so that's plus 2. And there we go. You know what I want to do? I'm actually going to show you the graph of this implicit curve. It actually is an ellipse shape. It's an elliptical shape, which is kind of like an oblong circle. And I'm going to plot this point, and I'm going to graph this line and show you that it will indeed be tangent to this curve at this point. So that's really a way you can actually check that this is the correct answer by using some graphing technology. So let's take a look at that graph. All right, so I'm actually using this app called Desmos, and you can actually go to the website desmos.com. And it's just a graphing calculator, and it's nice because we can just type in really any curve. And this example was x squared plus xy plus y squared equals 3. And I wanted to show this with the TI-83. The problem though with the TI-83 is that you need to have y solved for. And I mentioned you could solve for y, but it's kind of tricky. So I'm not going to show that. In fact, I'm just going to show with some graphing calculator online, and the best one I like is Desmos. So notice we get indeed this ellipse, this nice ellipse shape, but it's kind of tilted. Usually you see ellipses that are either horizontal or vertical, but this one's rotated, which is kind of cool. And the point we had, our point of tangency was 1, 1. And if our answer was correct, as soon as I type in our answer, which is that line, it'll pass through this point and just touch the curve. So it'll be tangent to the red curve, and it'll pass through that blue point. So let's take a look. Our answer was y equals negative x plus 2. Boom, look at that. So that green line passes through that blue point, tangent to the red curve. So that's all I wanted to show here, but it's a nice demonstration that with graphing technology, you can check your answer actually to see if the tangent line that you got, the equation you got, is indeed the equation to a tangent line of a particular curve at a particular point. So now I'm going to move on to something new. All right, so here are the new rules that are basically consequences of implicit differentiation, and they are, of course, inverse trig functions. So now we can take derivatives of inverse trig functions, and these are the rules. So these are just straight up what their derivatives are. Now, well, first off, we have the 3 usual ones: sine inverse, cosine inverse, and tangent inverse. And we have the oddball ones: cosecant inverse, secant inverse, and cotangent inverse, which I'll just tell you right now, never really come up at all. So I wouldn't devote any memory to these 3 at all, but that's just me. These do come up. The most important one I think that comes up very often in calculus is the third one here. And the other ones may come up from time to time, but this one comes up way more often, from what I've seen anyways. And I'll actually prove that to you. I'm not going to prove all 3 of them or even all 6 of them, but I do want to say that there's some patterns here that you can kind of take note of. Notice the derivative of sine and derivative of cosine. What's the connection? Is that cosine is negative that of sine. And actually the same thing is true for tangent to cotangent. Its derivative, the derivative of cotangent, is inverse, is the same as the derivative of tangent inverse, but negative. In fact, that's even true for secant and cosecant. So we can say for any trig inverse function, whatever its derivative is, its cofunction, or co-inverse function, however you'd say it, is just negative that answer of that result. And that's all I really want to say as far as pattern goes. The other thing that I should probably mention is there is alternate notation. Just for example, let's say you see sine inverse of x. So again, there's of that I'm omitting here just because it'd be too many parentheses. But instead of sine inverse, the other way of notating this is arc sine. The reason why a lot of these weird alternate notations occur is kind of sad, but basically it's the technology at the time. So when mathematicians would type things with typewriters, very often it would be difficult for it'd be difficult for the typewriters to show exponents, because you'd have to, you could do it possibly, but the real way that you'd want to do it is you want to make the negative one small and it's even if you could do it, it's a little bit of a hassle. So just to kind of avoid that headache, people just use arc signs. So that's essentially the reason why there are those notations. And I'm going kind of on a tangent here, no pun intended. But another alternate notation is e to the x. Some people write as exp of x, which is nice because we see that it function itself, it's the exponential function. So rightly named so, exp for exponential. But anyways, like I said, I was going on a tangent. So let's prove the derivative of arctangent or tangent inverse. And here's how I'm going to do it. The first thing I'm going to do is I'm going to call this y. So y is tangent inverse of x. And here I'm writing the parentheses. Now, if you don't remember, inverse functions, in fact, not just trig functions, but any inverse function has the following property. If you apply the original function to the inverse, it undoes that, they cancel, and you just get the inside. So namely, if we take tangent of both sides of this equation, on the left we get tangent of y, on the right we get tangent of tangent inverse of x, and according to what I just said, what will happen is the tangent and tangent inverse will cancel. So let me cancel these out. And you just get x. So now we have tangent of y is equal to x. Perfect. Now, a few things here, and in fact, before I begin, let me just say we're like a few steps away from completing this proof. And then we can do some examples involving these finally. But the first thing I want to say is that here, tangent of y represents an angle. Any trig function is always taken of an angle, and the result is some ratio. So x we can write as a fraction x over 1, and just recall that here this y is treated as an angle, so that's my symbol for angle. So what I'm going to do is I'm going to create a right triangle with angle y, okay? And tangent, if you don't remember, is opposite over adjacent. So here we're treating the numerator of this fraction as the opposite side of the right triangle, and the denominator as the adjacent side of the triangle. Perfect. So I'm going to label this as x, label this as 1. So tangent of y is indeed x over 1, which is x, so that's true from this equation here. And if we wanted to find the hypotenuse, we could, using Pythagorean theorem. Recall that this squared plus that squared is a hypotenuse squared. So 1 squared, which is 1, plus x squared is equal to this squared. So this would have to be the square root of 1 plus x squared. And let me just say that the proofs for any other of the trig inverse functions follows the same pattern. So if you try to prove any of these other ones, let's say sine or cosine by yourself, if you follow this as a guideline, you'll see that it'll be exactly the same process. So now the last and final step, well, kind of last and final step here, is to look at our equation tangent of y equals x and to differentiate implicitly. So the derivative of tangent of y, let me just write that over here, is secant squared of y. Now remember, since it's a function of y, when you take its derivative, you need to multiply by what? By y prime. And that's it for the left side. For the right side, derivative of x is just 1. And now finally solving for y prime, we just divide by secant squared. So y prime will be 1 over secant squared. And you can just, I guess, apply this here to find secant of y, square it, and then take 1 over that. And yeah, I'm going to do that. I was going to say another thing you can do is you can write 1 over secant squared as just cosine squared, because the inverse of secant, of course, is cosine and vice versa. But it's actually okay to do that here. Notice cosine is adjacent over hypotenuse, so it's 1 over this. So secant is its reciprocal, this radical over 1. Anything over 1 is just itself, so we're going to get this radical. Since it's squared, squaring the radical cancels, and we get the result we were looking for. So we'll now get the dy dx, which is just what we're looking for, derivative of tangent inverse, is 1 over 1 plus x squared. Because again, squaring secant, which is this radical, cancels the radical and gives us that in the denominator. So there we go, that completes the proof. And the check mark didn't make it onto the screen, but I wrote a check mark. Let me just do it there for completion. Or if you like, I can do this box here, meaning we're completed with the proof. Proof is done. And now we can move on and do some examples involving these rules. Let's take a look. All right, so now for the last two examples we'll be seeing in this section. We're first asked to find the derivative of sine inverse of x squared, which is just a normal equation involving, well, the chain rule. So let's take a look. So its derivative, dy dx, will be, well, let's see, derivative of sine inverse we just saw is 1 over the square root of 1 plus the inside squared. The inside in this case is x squared, and then by chain rule we have to multiply this by derivative of the inside. Derivative of x squared is 2x, so in total we get this as our answer. 2x over the square root of 1 plus, well, let's see, x squared is just x to the 4th. So there we go, and I'll box that. So that was kind of interesting, but yeah, this next one is going to be a lot more. So this is an implicit differentiation, implicit equation. So we're going to solve implicitly, of course. And we're just going to start first by taking derivative of each side. Derivative of the left, tangent inverse, we already saw that rule. Derivative of tangent inverse is 1 over 1 plus the inside squared. But by chain rule, we have to multiply it by derivative of the inside. Derivative of x squared y is a product, and it requires, of course, the product rule. Derivative of the first, x squared, is 2x. Regular of the second, y, plus regular of the first, x squared, times derivative of y, which is y prime. Notice again, we only get y prime when we touch a term involving y, as far as derivatives go anyways. So now on the right, derivative of x is 1. Derivative of xy squared, again, we need the product rule. Derivative of the first is 1. Regular of the second is y squared, so no y prime there because we're not taking derivative of a function of y. But now we will, because for the second part of this product rule, we'll have regular of the first times derivative of the second, which is 2y, and yes, now we get a y prime. Perfect. Well, kind of perfect. This is a little bit of a mess. So what I'm going to do now is I'm just going to move things around. I mean, we kind of know what to do here. Distribute this, save this guy here, because it's a y prime term. Subtract to that side after subtracting this to that side. So I may leave out a little bit of steps, but just kind of try to follow me. So after distributing this, the only one we're going to keep is this term after distribution, which is going to be x squared over 1 plus, if you distribute this power, you get x to the 4th y squared times y prime, okay? Minus, this guy I'm going to subtract over here, and I'll write that as, let's write it like this, 2xy y prime, okay? Equals, so now we have these two terms stayed on that side because they're non-y prime terms. So that's 1 plus y squared. And this guy that I didn't underline after distribution is a non-y prime term, so we're gonna subtract it to the right. So minus 2xy over 1 plus x to the 4th y squared. Whew. I hope we followed that. You can go through it in more detail, but there it is. Now finally, factoring a y prime out. Well, a y prime outside of this crazy fraction, x squared over 1 plus x to the 4th y squared minus 2xy equals 1 plus y squared minus 2xy over 1 plus x to the 4th y squared. Yikes. All we need to do now is divide by this and we'll be done, but I want to go a little further and simplify. Of course, I'm completely out of space, so I'm going to rewrite this last line up here and erase everything else. So let's do that and let's see how crazy it gets. Right, so there it is. I shifted it up and erased everything else. And finally, we're going to divide by this guy here to get y squared by itself. I kind of don't want to write it in that detail, but I'm doing it, so that's fine. Divide that to both sides. X squared over 1 plus x to the 4th y squared minus 2xy. These cancel, so we just get y prime is equal to that. Now, instead of rewriting it, I want to simplify this a little bit because it kind of annoys me. Why does it annoy me? It annoys me because we have a fraction over a fraction, or at least terms involving fractions. So one way we can do this is, well, we can combine into one fraction on top and bottom, and then multiply top by the reciprocal of the bottom, but that's too much. A better way of doing it is multiplying top and bottom of this one huge fraction by something that will get rid of all fractions. And in this case, what we're going to multiply top and bottom by is just the common denominator that we see here, the quantity 1 plus x to the 4th times y squared. Just like that. Now, in doing so, this distributes here, here, and here. When it distributes here, it cancels out, so that's fine. When it distributes here and here, for the first one, it cancels out, and that's fine. But we legitimately have to do distribution for the other terms, though. So let me show that. So this times 1 in the top is just going to be 1 plus x to the 4th y squared. This times y squared is going to be y squared distributed into each of these, which is kind of funny. So we get plus y squared plus x squared y to the 4th minus the only thing that survives in the second term here, or I guess the third term really, is 2xy. And notice there's no terms to combine on top, so we're good. So I hope that was okay. Now for the bottom, well, let's see. For the first term, there's cancellation and we only have x squared. Perfect. Here, we're going to have negative 2xy times this quantity, so I'll distribute this 2xy into each of these. Negative 2xy. So we'll get negative 2xy times 1, and then negative 2xy times x to the 4th y squared will add 4 and 2 to those powers, because these powers are 1. So it's 5 and 3. Perfect. There may possibly be some other simplification you can do. I'm not going to bother. I'm happy with this. The only thing is I'll call this y prime dy dx to finish it off because, of course, the example said find dy dx. Didn't say solve for y prime. But hopefully in this example you can kind of see what I was saying earlier. Writing y prime will save us a lot of writing throughout. But at least at the end we can write dy dx because we have the recognition that they are the same thing, just different notations. Well, fantastic. So that includes 3.5. I really hope you enjoyed it. I know I sure did, like always. And I'll see you in the next video for 3.6. That's going to be a lot of fun. I'll see you there. Thanks for watching.